Download this code from codegive.com, link in the description below. Amateurs crack a 30-year-old math problem, a deep dive and practical exploration. For over 3 decades, a perplexing problem in mathematics, concerning a specific type of geometric structure known as aperiodic monotiles, resisted all attempts at solution. In 2023, a seemingly unlikely breakthrough occurred. An amateur mathematician, David Smith, stumbled upon a potential solution. Working with a team of computer scientists and mathematicians, including Craig Kaplan, Chaim Goodman-Strauss, and Siobhán Roberts, they were able to verify and formalize his discovery, culminating in the creation of the first known aperiodic monotile, dubbed the hat. This wasn't just a lucky guess, it was a fascinating interplay of intuition, perseverance, and, crucially, computational exploration. This tutorial will delve into the details of this remarkable achievement, explaining the underlying mathematical concepts, the methods employed, and provide you with examples of how you can explore similar problems using code. 1. Understanding the core concepts, aperiodic tiles and monotiles. To appreciate the significance of this discovery, let's break down the key terms. Asterisk tile. Asterisk a tile is a shape that can cover a plane without gaps or overlaps. Think of bathroom tiles or tessellations in artwork. Asterisk tiling. Asterisk a tiling is a pattern of tiles that covers a plane without gaps or overlaps. Asterisk periodic tiling. Asterisk a periodic tiling repeats itself in a regular, predictable pattern. You can shift the entire tiling horizontally or vertically by a certain distance and it will look exactly the same. Think of a checkerboard pattern. Asterisk aperiodic tiling. Asterisk an aperiodic tiling covers the plane, but never repeats itself in a regular pattern. You can't shift it and make it look the same. Penrose tilings are a well-known example of aperiodic tilings, but they use 2 different types of tiles. Asterisk monotile. Asterisk a monotile is a single shape that, when used repeatedly, can tile the plane. Think of a square or a regular hexagon. A monotile is aperiodic if it can tile the plane, but only aperiodically. The Holy Grail, the aperiodic monotile. Mathematicians had long wondered if an aperiodic monotile existed. This is a single shape that can only tile the plane in a non-repeating, aperiodic way. Until 2023, no such shape was known. Many different sets of tiles had been discovered that could only tile aperiodically, like Penrose tiles, but none were found that contained only a single shape. 2. The hat, a breakthrough aperiodic monotile. The hat is a 13-sided polygon formed by joining 8 equilateral triangles. The key to its aperiodicity lies in its forced arrangements and the relationships between its internal angles. The hat can only tile the plane by creating larger and larger complex patterns that never repeat. 3. How they did it, a blend of intuition and computation. The discovery of the hat wasn't solely based on rigorous mathematical deduction. It was a process that involved intuition and exploration. David Smith, a retired printing technician with a passion for tiling, experimented with different shapes, cutting them out of cardboard and arranging them. He noticed intriguing patterns arising from a specific shape based on hexagons. Computational verification. Smith collaborated with computer scientists who could computationally verify that the hat indeed tiled the plane and, more importantly, that it did so aperiodically. Mathematical proof. The team then rigorously proved mathematically that the tiling generated by the hat is inherently aperiodic. The power of computation. The computational aspect was vital. It allowed the team to visualize large tilings. Computers can generate and display vast arrangements of the hat tiles, providing visual confirmation of its tiling properties. Explore constraints and rules. They could program rules and constraints that govern how the tiles interact, simulating the tiling process and identifying potential issues or patterns. Test hypotheses. Computers enabled rapid testing of different tiling strategies and variations of the hat shape. Identify emerging patterns. Analyzing the large-scale tilings generated by the computer helped in identifying and formalizing the underlying mathematical principles that govern the aperiodic behavior. 4. Exploring aperiodic tilings with code. Python example using matplotlib and basic geometry. While simulating the exact aperiodicity of the hat is complex, we can explore simpler aperiodic tilings programmatically to get a sense of the underlying concepts. Let's consider a basic example, generating a Penrose tiling, which, remember, uses two types of tiles, but illustrates the aperiodic principles. Explanation of the code. 1. Libraries. Imports matplotlib for plotting and numpy for numerical calculations, especially angles and coordinates. 2. Golden ratio. Defines the golden ratio phi, which is crucial in Penrose tilings. 3. Tile definitions. Thin_rhombus, and thick_rhombus, functions define the vertices of the two types of rhombus tiles, based on their acute angles, 36 and 72 degrees. They accept an origin to shift the tile and a scale to adjust the size. 4. Draw_rhombus, this function takes an axis object, the vertices of the rhombus, and a color, and draws the rhombus on the plot. 5. Generate_Penrose_tiling, this function implements a simple, and incomplete, Penrose tiling algorithm based on substitution rules. It starts with an initial set of tiles, in this case, one of each rhombus type. For each iteration, it applies substitution rules. Each tile is replaced by a set of smaller tiles according to specific rules derived from the golden ratio. This substitution is key to the aperiodic nature. These rules are simplified in this example. The code loops through the existing tiles. Critically, it checks the array values directly, np.all, tile == thin_rhombus. This comparison needs to be an exact match because Python does not easily allow you to say this tile is a copy of this function call. 6. Plot setup. The code sets up a matplotlib plot, disables the axes, and sets the aspect ratio to equal to avoid distortion. 7. Tile generation and plotting. It calls generate_Penrose_tiling, to generate the tiles. It loops through the generated tiles and calls draw_rhombus, to plot them. 8. Display *plt.show, displays the generated tiling. Important notes about this example. Simplified substitution rules. The substitution rules implemented in this example are highly simplified. A proper Penrose tiling algorithm involves more complex rules based on orientations and matching rules. This version focuses on demonstrating the basic principle. Incomplete tiling. This code generates only a small portion of a Penrose tiling. To create a larger and more complete tiling, you'd need to implement more sophisticated substitution rules and potentially use recursive functions. Aperiodicity. The aperiodicity isn't visually obvious in this small example, but the underlying substitution rules are designed to prevent the tiling from repeating perfectly. Running the code. 1. Make sure you have matplotlib and numpy installed. If not, install them using pip install matplotlib numpy. 2. Copy and paste the code into a Python file, example penrose.py. 3. Run the file from your terminal, python penrose.py. You should see a window displaying a simple Penrose tiling. Experiment with the iterations parameter in generate_Penrose_tiling, to see how the complexity of the tiling increases. 5. Going further, simulating the hat. Simulating the hat tiling is significantly more challenging than Penrose tilings due to its complex geometry and tiling rules. Here's a conceptual outline of how you might approach it, along with potential Python libraries to use. Asterisk representing the hat asterisk. You'll need a precise representation of the hat geometry. You can use the coordinates of its 13 vertices. Shapely library is excellent for handling geometric objects and their transformations. Asterisk tiling rules asterisk. The hat tiling involves specific matching rules based on its shape and orientation. You'll need to encode these rules in your code. This is the most challenging part. You need to define how two hats can touch without overlapping. Asterisk tiling algorithm asterisk. A possible approach is to start with a single hat and then iteratively add neighboring hats based on the tiling rules. This requires a collision detection algorithm to prevent overlaps. Asterisk collision detection asterisk. Check for overlaps between tiles. Shapely can also help here with methods like intersects, to detect if two polygons overlap. Asterisk orientation and transformations asterisk. You'll need to be able to rotate and translate the hat to different positions and orientations. Shapely provides methods for these transformations. Asterisk visualization asterisk. Use matplotlib to visualize the growing tiling. Code snippets, conceptual. Challenges in simulating the hat asterisk. Asterisk complexity of tiling rules asterisk. The hat tiling rules are intricate and difficult to translate into code. Asterisk computational cost asterisk. Simulating large hat tilings can be computationally expensive due to the collision detection and geometric calculations involved. Asterisk enforcing aperiodicity asterisk. It's difficult to guarantee that the algorithm will only generate aperiodic tilings. You'd need to analyze the resulting tilings to confirm their aperiodicity. 6. Lessons learned, the importance of interdisciplinary collaboration. The hat discovery highlights the importance of amateur contributions amateur mathematicians and enthusiasts can make significant contributions to research. Computational exploration computation is a powerful tool for exploring complex mathematical problems and generating hypotheses. Interdisciplinary collaboration the collaboration between mathematicians, computer scientists, and enthusiasts was essential for the success of this project. 7. Conclusion. The discovery of the aperiodic monotile the hat is a testament to human ingenuity and the power of computational exploration. While replicating their work completely is a complex undertaking, this tutorial has provided a glimpse into the underlying mathematical concepts and a starting point for exploring aperiodic tilings using code. The combination of intuition, rigorous mathematical analysis, and computational power demonstrates a powerful approach to tackling challenging problems in mathematics and beyond. This example should inspire you to use your own computational skills to explore and perhaps even contribute to solving unsolved problems in science and mathematics.